The engineering of carbon nanotubes. Why the strongest material ever discovered is still almost impossible to use. Opening hook, the problem. In 1991, a materials scientist looked through an electron microscope and found something that, on paper, should not exist. It was stronger than steel, lighter than aluminum, more conductive than copper, and stable at temperatures that would melt most metals. And yet, more than 30 years later, this material still hasn't changed the world. Carbon nanotubes, often called CNTs, are theoretically one of the most perfect engineering materials ever discovered. If their properties could be scaled up reliably, they would redefine aircraft, batteries, electronics, medicine, and even space structures. But they haven't, because the problem isn't discovering carbon nanotubes. The problem is engineering them. Visual, electron microscope image zooming into a carbon nanotube lattice. Part 1. Context. Why we want carbon nanotubes. Modern engineering has hit a wall. Aircraft are limited by weight. Batteries are limited by energy density. Electronics are limited by heat dissipation. Structural materials are limited by cracks, tiny, invisible cracks that grow until failure. Carbon nanotubes promise to attack all of these problems at once. At the atomic level, a carbon nanotube is simply a sheet of graphene, one atom thick, rolled into a cylinder only a few nanometers wide. But that geometry changes everything. Visual, graphene sheet rolling into a nanotube animation. Because when carbon atoms bond in this configuration, the strength of the covalent bonds aligns almost perfectly with the direction of applied force. This isn't just strong material. This is near theoretical maximum strength, dictated by quantum mechanics. To put that into perspective, steel fails at around 1 to 2 gigapascals. Carbon nanotubes exceed 60 gigapascals. That's not an incremental improvement. That's a phase change in engineering capability. So why aren't airplanes, bridges, and rockets made from them? Because physics giveth, and physics taketh away. Part 2. The physics constraint, strength versus scale. At the atomic scale, carbon nanotubes are nearly flawless. At the human scale, they fall apart. This is the central engineering paradox. The strength of a material is not determined by its strongest bonds, but by its weakest defect. Visual, chain analogy animation, breaking at weakest link. In steel, defects are grains, impurities, and dislocations. In carbon nanotubes, defects appear during growth, missing atoms, misaligned bonds, uneven chirality. One missing atom in a nanotube doesn't just weaken it slightly. It creates a stress concentration that propagates like a crack. And here's the brutal truth. The longer the nanotube, the higher the probability that a defect exists. This is not a manufacturing problem alone. This is a statistical inevitability. Perfect nanotubes exist, but only at microscopic lengths. Part 3. Why nanotubes are so strong. First principles. To understand why carbon nanotubes are special, we need to go down to the electron level. Carbon atoms form sp superscript 2 hybridized bonds, creating a hexagonal lattice. These bonds are among the strongest known in nature. Visual, sp superscript 2 bonding diagram with electron orbitals. In a nanotube, bonds are aligned with the axis of force. There are no grain boundaries. Load is distributed evenly across the lattice. Compare this to steel, where grains interrupt force paths. Dislocations move under stress. Cracks grow unpredictably. Carbon nanotubes don't yield like metals. They hold until they catastrophically fail. Which brings us to the next problem. Part 4. The manufacturing nightmare. Making carbon nanotubes is easy. Making useful carbon nanotubes is not. Most CNTs are grown using chemical vapor deposition, or CVD. Visual, CVD reactor animation showing gas flow and catalyst particles. Hydrocarbon gas flows over metal catalyst particles. Carbon atoms deposit and self-assemble into tubes. But this process creates chaos. Different lengths, different diameters, different chiralities, twist angles. Chirality matters because it determines whether a nanotube is metallic, semiconducting, or electrically useless. Right now, manufacturing CNTs is like producing millions of wires where some conduct electricity, some don't, and none are the same length. Imagine building a circuit like that. Part 5. Debunking this supermaterial myth. Carbon nanotubes are often marketed as a miracle material. They are not. They are a miracle in theory and a nightmare in practice. For example, individual nanotubes are incredibly strong. CNT composites are only marginally stronger than carbon fiber. Why? Because strength doesn't transfer efficiently across nanotube boundaries. Visual, force transfer diagram between nanotubes versus continuous fiber. Load must move. Nanotube, resin nanotube. Each interface wastes energy. This is why CNT cables are not replacing steel cables, and why the famous space elevator remains science fiction. Part 6. Electrical and thermal promise. Where CNTs shine is not bulk strength, but transport phenomena. Electrons travel through nanotubes with minimal scattering. Heat moves ballistically along their length. Visual, electron flow animation inside nanotube. This makes CNTs promising for heat spreaders in electronics, high-frequency transistors, battery electrodes. In lithium-ion batteries, CNTs improve charge rate, mechanical stability, cycle life, but again, only in small amounts, because scaling up means reintroducing defects. Part 7. Health, safety, and toxicity. There's another uncomfortable reality. Carbon nanotubes behave, biologically, like asbestos. Long, rigid nanotubes can lodge in lung tissue and resist breakdown. Visual, comparison between asbestos fibers and CNTs. This doesn't make CNTs unusable, but it adds cost, regulation, and risk. Engineering isn't just about what can be built. It's about what can be built safely, repeatedly, and cheaply. Part 8. The hero solutions, partial, not perfect. Engineers are fighting back in 3 main ways. 1. Short CNT reinforcement. Using CNTs as additives, not primary structure. 2. Aligned CNT forests. Growing vertically aligned arrays to improve load transfer. Visual, SEM image of CNT forest. 3. Hybrid materials. Combining CNTs with graphene, polymers, or metals. None of these unlock the full theoretical potential, but they work within physics, not against it. Part 9. Economic reality. Carbon nanotubes cost anywhere from $100 per kilogram, low quality, to thousands per gram, high purity. Compare that to steel at under $1 per kilogram. Until defect control improves by orders of magnitude, CNTs will remain specialized, strategic, not structural. Final verdict. Carbon nanotubes are not overhyped. They are underengineered. They reveal a deep truth about materials science. Nature allows perfection at small scales, but punishes it at large ones. CNTs will change technology, just not in the dramatic, sci-fi ways often promised. And that's not a failure. That's engineering. Because real progress isn't about defeating physics. It's about learning how to work within its limits. Visual, fade from atomic lattice to real-world device.